Talk about the head-gated number of graphs. So the plan is as follows. I will first give a very quick overview of the existing literature using slides, and then I will turn to write proofs on blackboard. So this is based on a journal work with Noga alone and Omri when you read. So Omri was a former PhD student of Noga at Tel Aviv. So now he is a postdoc at MIT. And also Zaki Tamer, who is my postdoc host when I was in Tel Aviv. Okay. So let's begin with some introduction of what is the head-guessing game. So here is a small example. So assume you have two players and two colors. And each player can see the head color of the other player, but not his or her own. So each player should, some guy put some head color on the heads. So and each player should guess his or her own head color based on the color they see, right? Because this is the question. So can we design a guessing strategy such that for any color assignment, at least one of the players guesses correctly? So for example, Alice can see the head color of Bob. So based on the color of Bob, Alice should guess her own head color. And similarly, Bob can see the head color of Alice. And based on Alice's head color, Bob should guess his own head color. So you see the players win if at least one of them make a correct guess. So two players, two colors. Can you design a winning strategy for the players? Actually, the answer is very simple. So basically, Alice and Bob just guesses oppositely. So Alice guess every time. Alice guess that so her head color are the same as Bob. So Bob guess his head color is opposite with Alice. So at least one of the players must make a correct guess. So the players win. And this can be generalized to N players and Q colors. For example, you can imagine a complete graph on N vertices, and every player sits on every vertex. So the rule is that each player can see the head colors of the other players, but not his or her own. So each player should guess his or her own head color based on the colors they see. So basically based on the head colors of the neighbors. So the question is, for which N and Q, there is a guessing strategy such that for any color assignment, at least one of the players guesses correctly. So the answer is Q, at least for, if Q is no larger than N, there is always exists winning strategy for players. Why? So the guessing strategy is also very easy to describe. For example, if Q equals to N, so one may identify, so there are N players, N colors. So we can identify colors as numbers in Zn, right? 1 to N minus 1. So we can use a vector X. So it's a vector of length N. So be the vector of the color assignment. So Xi is the color assigned to the ith player, right? So the ith player simply guesses that the summation of the Xi equals I, right? Or in other words, the ith player just guesses that his or her head color Xi equals I minus this summation modulo N, say. So then obviously at least one player make a correct guess, right? Because this summation has to be equal to some I modulo N, right? So at least one of the players must make the correct guess. So but what happens if the number of colors, say Q, is larger than N? So we can show that if Q is at least N plus 1, then there must exist a color assignment such that no player make correct guess. So you just random colors, you just assign colors randomly to the players. So then for every fixed guessing strategy, each player guesses correctly with probability just 1 over Q, right? This is because, so for example, this is the ice player. The ice player's guess is based on the color assignment of the N-1 other players. So once the colors of the other N-1 players are fixed, his guess is fixed. His guess is fixed. So with probability 1 over Q is equals to the color assigned to him. So each player guesses correctly with probability just 1 over Q. And so the expected number of correct guess is N over Q. So it's smaller than 1 if Q is at least N plus 1. So this means that there must exist some color assignment that all players are wrong. So this basically answers this question. So if Q is no larger than N, then there is always a winning guessing strategy for the players. So yeah, this toy example can be generalized for any graphs. So for example, so this is the starting of the general head guessing game. So we have N players and Q colors and a connected graph G on N vertices. So just imagine that every player sits on every vertex. So each player can only see the head colors of their neighbors, but not his own. So all players should guess simultaneously, so their own head colors, based according to a predetermined guessing strategy and the head colors they see. So basically based on the head colors of their neighbors. And the guessing strategy is known to all players, so they can determine before the game starts. So we say that the players win if there is a guessing strategy such that for any color assignment, there is at least one player guesses correctly. So we define the head guessing number of G, so Hg of G, to be the largest Q, such that there is a winning strategy for the players. So what we have just proved is that the head guessing number of Kn, the complete graph on N vertices, is N, right? Yeah, so there is also an algebraic formulation of guessing strategies. So given a graph G with N vertices and Q colors, so we label the colors like first Q positive integers, and we use this vector X, so it's a Q area vector of range N to denote the color assignments. So where Xi is the color assigned to Vi. So the guessing strategy Gi of the ith vertex. So the guessing strategy Gi of the ith vertex. So what is Gi? Gi is simply a function from the neighbors. So Gi is simply a function from a set of neighbors, like Q to the power of Ni. So Ni is the size of the neighbors of I to Q, right? So the guessing strategy of the ith vertex can be simply described as some function Gi. So from Q to the power of Ni to Q. So we write Gix to be the guessing of Gi. So where X is the color assignment. Then the N functions G1 to Gn form the guessing strategy. So which means that guaranteeing at least one correct guess, if and only if this function is vanishes over all Q to the power of Earth, right? So what does this function vanish mean? It means that there exists at least one I such that Xi equals Gi. So Xi equals Gi means the ith vertex guesses his head color correctly. So this is an algebraic formulation of the guessing strategy. So this formulation is sometimes helpful because it allows us to use some algebraic tools. For example, combinatorial Nash analysis to study the head-guessing game. So there are several other versions of the head-guessing game. Indeed, the head-guessing games become popular in like 2001. So there is an article in New York Times with the title "Mathematicians Now Care About the Head Colors." Then this game become popular. And there are many versions of head-guessing game. For example, in some variations, so each player can guess or just pass. So it's like just like a board game. You can guess or pass. So and players win if at least one player guesses correctly and no one guesses wrong. So yeah, there are some different rules for the head game. So in other variations, players are even allowed to guess sequentially. So they do not have to guess simultaneously. They can guess sequentially. And the players cannot pass. So, and the objective is to guarantee as many correct guesses as possible. So there are many variations. So let's focus on our problem. So what is known about the head-guessing numbers? So for which graph G is head-guessing number is known. Figure determine that so head-guessing number of Kn is n, just as we said. So Dr. Jahari, Krenbeck, and Rayton showed that the head-guessing number of trees are 2. Is 2. And for cycles, it is known that the head-guessing number of a cycle is 3 if n equals 4 or n is n or 3 divides n. Otherwise, the head-guessing number of Cn is 2. So also, it is known that the head-guessing number of K33 so is 3, and the book graph. So the head-guessing number of book graph and the windmill graph are also known. So book graph BDN looks like follows. So this is BDN. So you have a click on D vertices. This is KD, and you have n vertices here. This is n vertices here, and this is a complete bipartite graph connecting them. So this is a book graph. The windmill graph looks like follows. What is like WDN? It's like you have many disjoint copies of KD. So you have n so disjoint copies of KD. And then you group one vertex together. So it's like a windmill. So if n is sufficiently large, then the head-guessing number of these two graphs are known. And also for some other complicated graph, GDN is known. So it's constructed by some n-array tree, something like that. Also, another natural direction is to explore the head-guessing number and other graph parameters. So they want to know, for example, what is the head-guessing number for bounded degree graphs? So this is a very natural question. Can we bound the head-guessing number in terms of the maximum degree, say delta? So by a standard application of the local lemma, Fernick shows that for every graph of maximum degree delta, the head-guessing number is at most E times delta. So, and he even conjectures that the head-guessing number cannot exceed maximum degree plus 1. For example, it holds for clicks and cycles and trees. But this conjecture was disproved recently. So these two authors they construct the graph G such that its head case number is at least 4.3. So it just disproves this conjecture. And now the recent conjecture is that can we improve the upper bound can we improve the upper bound from the local lemma by some epsilon, so by some constant epsilon. So this is the recent open problem. So also we are concerned about the head case numbers of bounded degeneracy graphs. For example, if a graph is degenerate, can we bound its head case number? So this question is still open. But on the negative side, Hurley showed that there is a sequence of graphs, a sequence of degenerate graphs. So the head case number can be as large as the double exponential of d. So if we can bound the head case number in terms of the degeneracy, then the function should be at least double exponential. So also people are interested in to bound the head case number of planar graphs. So there is open question so that can we bound the head case number by a constant if G is a planar graph. So this question is still open. So and also there are some constructive lower bounds. For example, Aron and Schutzever shows that there exists some planar graph G with head case number at least 12, and this lower bound has been improved to 14 and 22. So 22 is the current record. And for some other, and there is an important result recently. So Bradshaw shows that the head case number of is bounded if the graph is not only planar but also out-planar. Okay, so these are basically some review of existing results. So our motivation to study this problem is that we know we want to find some graph with large head case number. So from the previous examples, we know that the head case number is at least as large as the clique number, right? If G contains a clique of size n, then the head case number is at least n. So, and we want to show, and we want to know that if there exists graphs with large head case number which tends to infinity, but constant clique number. For example, what is the head case number of complete bipartite graphs? So the complete bipartite graphs has only clique number 2. And in fact is a classic problem and well-studied problem in this area. For example, so in 2008, it is Buckler et al. Shows that the head case number of the complete graphs is like of the order, at least of the order log n. And the names are very hard to pronounce. Yeah. So and these two mathematicians are able to remove log. So it's a result in 2015, and there is an open problem from Butler's paper. They asked that if the head case number of Kn is at least n to the power of c for some constant c. So we, in fact, resolved this open problem. We show that the head case number of complete R-partite graphs. So here, this R means there are R-partites. So we show the head case number of complete R-partite graphs is at least n to the power of 1 minus R over 1 minus little r over 1. So which implies that the head case number of Kn is at least n to the power of 0.5 minus 1. And I will give a proof of this result soon. So and here is an open problem. So we want to determine what is the correct order of the Hesse number of Kn. So it's lower bounded by root n, or it's at the most little of root n. So yeah. Okay, so I
What is
will.
the best now upper bound?
Upper bound is like upper bound is linear in n, right?
Linear.
Yeah. Because because for every graph of n vertices, the Hesse number is at the most n. Yeah.
So there is no sublinear upper
No,
bound.
there's
for
no
this.
sublinear upper bound. I think the first known upper bound is like n for Kn is like n plus 1. So sublinear upper bound is not known. Okay. Now I will use breadboard to give a proof for the lower bound of Kn. So can we just erase this? So any questions so far?
Did you mention about random graph at facing?
There are some results on the random graphs. Yeah. So see, for example, for GNP, if P is a constant, then the Hesse number is like I think it's n to the 1 minus little of 1 is high probability. Yeah, something like that. Okay. So I will present the proof of the following. The Hesse number of complete bipartite graphs is at least n to the power 1.5 minus of 1. So I will give you the guessing strategies for the vertices. So the proof is actually not hard. It's based on several easy observations and claims. So okay, let's begin some notations. So now we have a KMN. So we have an M here. This is a complete bipartite graph with M vertices on the left. So VL is of size n. So VR is of size n. And we have Q colors. Okay. So just imagine you have a this is VL, this is VR. So and we define color assignments. To VL and VR by two vectors. So this is chi of VR. So this is the color assigned. This is chi of VL. This is the color assigned to the vertices on the left. So this is a QRD vector of length m, right? And chi VR. It belongs to the set of QRD vectors of length n. So these are just the colors assigned to VL and VR. And we can also define the guessing strategies. So guessing, just remember that the guessing strategy of each vertex is simply a function of the colors they see. Yeah. So for VL, so we can define a guessing strategy like n functions f1 to fn. So fi is the Gaussian strategy for the ith vertex in VL. So here fi is the ith vertex. So he's getting strategy. What does the ith vertex see? He sees a vector of length n, right? Because he sees the coloring on the right is you have n colors, so it's a vector of length n. So it's a function from Q to n to Q. Similarly, for VL, for VR, so we can write there are n Gaussian strategies. So for G, G1 to Gn. So Gi is simply the Gaussian strategy for the ith vertex in VL. So for a vertex in the right, what does he see? He sees a vector of length m, right? A vertex here sees a vector of length n because he just sees the head colors of vertices in VL. So Gi is Q to m to Q. Also, given VL equals A, given a color assignments to VL, which is A vector of length n, and the color assignments to VR, so which is denoted by B, this is a vector of length n. What do we have? So the Gaussians of VL and VR are so the vectors in the pairs on the left just guess. So G of B, so is equal to G1. The first player's guess is G1B. The second player's guess is G2B. So no, this is F. This is F. This is the guess of VL. So the vector of length n. So the vertices in the right just guess GA because they say GA. They say the coloring A. So this is equals like G1A. Gn A. Okay. And we also need some notations from coding theory to characterize. So when players win. Okay, now we just need two very simple notations from coding theory. So for xy belongs to Q to n. So for two vectors, Q are the vectors of length n, we define a Hamming distance dxy to be the number of coordinates where they differ is I from 1 to n, such that xi not equal to yi. So, yeah, you just count if this is x1 to xn, and this is y from y1 to yn. You just count the number of i's such that xi not equal to yi. So, and this is the Hamming distance. This is Hamming distance. So we will also need a notion of a Hamming wall. Hamming wall. So the hummingbird is very easy. So B for a vector x and a positive integer r. So the hummingbird with center x and the radius r. So here is x, the center of the ball, and here is the r, the radius of the ball. So the hummingbird of center x and the radius r is simply the collection of all vectors y that have Hamming distance at most r from x. So it's just as in the Euclidean case. So these are all y such that dxy is at most r. Okay, this is all the notation we need. And this here is a very easy observation. Our first observation. One, to the players win. So remember that the players win if at least one of them make a correct guess. So players win if there are guessing strategies like this, some F and G, such that for any card assignment, chi VL equals A. So this is a vector of length N, and chi VR equals B, which is a vector of length N. What happens? Either so we can characterize the fact that so at least one player makes a correct guess using Hamming distance. So what does it mean that a vertex in VL makes a correct guess? It happens if the Hamming distance of if it happens that the Hamming distance of A, so if draw a new picture, and this is VL, this is VR. So given chi VL equals A, so here is the color assignment equals A, so it's A1 to AN, and the color assignment of R equals B, so we have B1 to Bn. So the guessings G of B are G1B to GMB. Oh, here is F. The guessings are F1B to FMB. So these are the guessings on the left. So the guessings on the right are the GA. So G1A to GNA. So clearly, if the vertices in VL make a correct guess, only if the Hamming distance between FB and A is less than F, right? So and the vertices in R makes at least one correct guess, and only if the Hamming distance between B and GA is less than N. So players win either the Hamming distance of A and FB is less than N, or so the Hamming distance or the Hamming distance of B and GA is less than n. Right? So we can characterize the winning strategy by using this Hamming distance. Okay.
There's one more behind.
Yeah, but so this is an easy observation. There are several other easy observations. For example, now let's focus on the guessing strategies of VR for a moment. So the guessing strategy of VR can in fact be represented by a matrix. So the G can be represented as an n times Q2M Q-ordered matrix. So what does the matrix look like? So here's a matrix M. Matrix M, it has n rows and Q2M columns. So you just label the rows by the function g. So there are n rows labeled by g1, g2 to gn. So the ith row is the guessing strategy for the ith vertex in VR. And the columns are there are Q2M columns. The columns are labeled by all possible colorings to VL. Right? There are in total Q2M possible colorings for the vertices in VL. So the columns are labeled by chi VL. For example, if a column is labeled by chi VL which equals A, then what do we put in this column? We simply put the guesses of the vertices on the right. So if the coloring for the column labeled by A, we assume the coloring of VL is A. Then the vertices on the right just guesses G1A, G2A, to GNA. Yeah, so the guessing strategies can be represented by the language of a matrix. This is very convenient. As follows. So, and we call, and this column is just GA. This column is just GA. Okay. So, and we can combine the first observation and the second observation. We combine these two observations, and we see when does VL fails. So, for example, if given the guessing strategy of VR, which is characterized by this M, now if your coloring of VR is B, if your coloring of VR is B, you just put it here, B1, B2, Bn. Then you can see from this matrix that so if this is B, so if the Hamming distance of GA and B is smaller than N, then it means that given chi VR equals B, if chi VL equals A, then the players on the right already win. So therefore, we only need to consider all the vectors such that the Hamming distance between GA and B is exactly n. So this makes the problem easier. So this is the third observation. Given chi VR equals B. So always remember B is a vector of length n. So we have basically we have two conditions. First, if the distance between B and GA is at most n minus 1, then chi VL equals A, we are already B. If the Hamming distance of B and GA is exactly n, then the coloring of VL is A. So we are all vertices in VR makes wrong guesses. So we say VR rules. Then we need to consider. In this case, we need to make VLV. So this observation motivates the following definition. So given a coloring of VR, say B, so we can, from this matrix, we can read the colorings of VL such that are bad for B. Right? Bad means the distance is n. So this motivates the definition. So given chi VR equals B, define. Yeah, please interrupt me if you have any question. So define a set of bad colorings with respect to B as maybe I just write here. It's C of B. So what is C of B? It's just the colorings here, A. It's just the colorings here on the left. Such that the distance of B and G of A is n. So the set CB is simply the colorings. The set CB is simply the colorings of VL that make VR loose. Right? So the good point is that given n, the set CB is known to all vertices in VL, right? Because this matrix is known to everybody, and every vertex on the left can see the vector B, right? So every vertex on the left can see B, and they can deduce CB from this matrix. So CB is known to all vertices on the left. So and we can make use of this information to design a guessing strategy for the vertices in VL. So it performs problems. So crucially, given chi VR equals B, CB is known to every vertex. So this is how we define a winning strategy. Claim 1, so winning strategy. Players win if for every chi VR equals B. So this set of bad currents with respect to B is contained in a Hamming ball of radius m-1. There exists some xb, which is a query vector of length n, such that what happens, this set cb is contained in a Hamming ball with center xb and the radius m-1. So if we can design a matrix with this condition, then we are winning. Why? So here is the proof. So we are going to make use of our first observation. So actually it's not hard. So we just define. So we need to define the guessing strategies F. So what is F? Fi simply equals Fib or Fib. Fib is the guess of the ith vertex on the left. So when he sees B. So the guess is simply the ith component, the ith coordinate of xb. So here, now fb equals what? Fb equals xb1, xb n. So fb is just the center of this Hamming ball. Fb the guess, so the guess on the left is just the center of the Hamming ball. Because, yeah, so then what happens? So let me write it here. So now I will argue for every A and B, at least one player makes the correct guess. Then for every IBL equals A, IBR equals B. So here, if A does not belongs to CB, this means that we are B, right? If A does not belong to CB, then by our previous discussion already means that we are B. Or A belongs to CB. If A belongs to CB, then what happens? So CB belongs to this Hamming ball, B xb m-1. So this is equals b fb minus 1. Then this is equivalent to saying that the Hamming distance of A and fb is at most m-1. Yeah, done. So we are. So in either case, we win. Okay. Yeah. So now the problem has turned into design matrix such that for every B, CB must be located in some Hamming ball of radius minus 1. So let's think about this problem. Say we have some vertices. So in a Hamming space or in a, maybe in a Hamming space, so we have a branch of vertices, and we want to put these vertices into a Hamming ball of radius m minus 1. So what can we do? So how can we guarantee that there always exists a Hamming ball of radius m minus 1 that covers all these points? Intuitively, this can be done if the number of points is not too many. For example, if there are only m points, then we can always find this Hamming ball. Why? So is the second claim. Any set of m vectors in Qm. Qm can be placed into a Hamming ball. Of radius m minus 1. Why? You just need to pick the center of this Hamming ball, right? So you have say you have vector 1, vector 2, vector m. So you view these vectors as row vectors. So here is your first vector, second vector. Here is your vector m. So how do you find the center of this Hamming ball? You just pick the stars on the diagonal, right? These m vectors must be located in a Hamming ball with this center and the radius at the most and minus 1, right? Because every vector, the Hamming distance, because the Hamming distance between the center and every vector is at most and minus 1, because they have a common coordinate. Right? Yeah. And so in order to show the existence of a matrix that satisfying the conditions of claim 1, we only need to make sure for every bit CB is at most n. Yeah. This in fact can be done. So this is the last claim. Claim 3. So pairs link. If there is an n times Q2m Q-early matrix and such that for every set of n columns, n plus 1 columns, there exists one row, a row that there exists a row that covers Q. So when restricting to these columns, so it is easier to draw a picture. Let's columns. Okay? So this matrix, this is a n times q2 n matrix. It has the following property. So for every set of m plus 1 columns, so for every set of m plus 1 columns, so you take any set of m plus 1 columns, there must exist some row I, such that when restricting to this row, so the coordinates of the columns restrict to this row must cover the entire alphabet 1 to q. So if one can find such a matrix, then we are done. Why? Because, so you go back to this. So we assume that such a matrix has a property that for any, so maybe I use a different color. So this matrix has a property that for any set of m plus 1 columns, there must exist row I, such that this row covers when this row must cover the entire alphabet Q. Then I claim that for such matrix and for every B, CB is at most n. Why? So given B, what is CB? So CB is just the columns that has Hamming distance n from B, right? CB is just the columns that have, so it's just the columns. Look here, CB is just the columns that have Hamming distance n from B. And if CB is at least m plus 1, then what happens? There will be a row such that BI must appear here, right? Because BI is an element of Q, right? So BI must appear here. So in particular, this column must have Hamming distance at the most n minus 1 from B. And this gives a contradiction. Yeah, so if such a matrix exists, then we have a linear strategy for K and N. And the existence of such matrix can be proved easily by the first moment method. So here's a fact. There exists such a matrix with M is of the order Q ln Q, and N is of the order Q square ln square. And we are done. So Q is like n to the power of 0.5 minus little of 1.
What did you write? Q log Q?
Yeah, Q ln Q. Yeah. M is Q ln Q. N is like M squared. Yeah. So this can be proved easily by the first moment method. And basically, yeah, I've finished the talk. Thank you.
Thank you. Any questions? So does your proof give a construction of such a matrix?
No, it's a existential proof. Yeah.
Do you think it's possible to find a concrete deterministic algorithm for players to come up with a strategy?
I'm not sure. It's about how it's about the efficiency, right? I don't know if there is a polynomial time to on the So you,
explicit.
of course, you can find the algorithm. You can find the strategy by brute force. But the time, but the complexity is huge.
Mhm. And when Q is prime or some particular thing, then is there like some easier constructions?
You mean when Q is prime?
Or
yeah. So
maybe Q is prime square, for instance.
yeah, actually,
Something like that.
it's a
Yeah,
very
some
interesting.
some interesting.
Yeah, it's a very interesting question. So as I just mentioned, the guessing strategies. So the guessing strategies is a function, right? It's a function like to the Q to the set of neighbors to Q. So actually, you can add extra restrictions to Fi. So you can see, you can add some restrictions saying that the degree of this function is not too large. So for example, if the degree is at the most 1, so then the guessing functions are called linear.
Mhm.
And in this case, we call the head guessing number like linear head guessing number.
Okay.
Yeah, something like that. And using combinatorial assurances, we can show that the linear head guessing number of any graph is at the of any D degenerate graph is at most D plus 1. That's something like that. Yeah.
So here you have the skewed case, m not equal to n. How do
Yeah.
you make it balance?
So actually, more versus the situations are even better. For example, if so, you can actually add any verses they do nothing. Yeah. So maybe a possible way to improve the bound is to make use of the other verses.
So what about hypercube? Seems natural thing to think.
Hypercube. Yeah, actually, I never thought about hypercube.
So looking at all these examples, it seems like when you have good expansion, it tends to be large.
Yeah,
When
yeah,
you have
yeah.
poor expansion, it's small.
Yeah.
But is it possible to prove, to link it to, I don't know, Cheever's constant or?
Yeah, actually, there's another open question saying that if there exists graph, so basically the question is like the Erdos graph. So the question is as follows. If for any pair of L and Q is for every pair of L and Q there exist graphs with say girth is at least L and the head guessing number is at least Q. There are some other questions like this. So it's related to the Erdos construction.
So it's actually even easier, right? My guess would be, say, constant degree expanding, probably that guessing number, I would guess polynomial. Yeah.
Polynomial, yeah.
Well, okay, that's very strong, but even a much weaker version will prove this one, right?
Yeah. Yeah, actually, the problem is very new. Like people don't know the connection between this head guessing number with other graph parameter. There are many things we need to be explored.
Probably two natural classes would be hypercube or these ND lambda graphs. Very,
Yeah, yeah.
They have very good properties. You know.
Is it this head guessing number is bounded by function of the trees or some
But by a function of what?
trees? Is it bounded by trees?
Trees.
Trees.
Tree width. Tree width. That's
I
the.
don't know what it is.
Okay, any other questions? So if not, let's thank the speaker.